Welcome again to the biostat course. Today we have the last topic, which is about correlation and rank correlation. Learning objectives of this lecture are: number one, understanding the concept of linear relationship between paired quantitative data. Understanding the concept of linear relation between paired quantitative data. Number two, using scatter plot to assess whether linear correlation exists and its direction. Number three, conduct formal hypothesis test to find the value and assess the strength of linear correlation, Pearson, and rank correlation, Spearman coefficient, using statistical software. Number four, compute and interpret the coefficient of determination. Again, we have understanding the concept of linear relation between paired quantitative data. Number two, using scatter plot to assess whether there is a relationship between two paired quantitative variable. Number three, compute and explain and test the hypothesis regarding the linear correlation coefficient of Pearson and the rank correlation coefficient of Spearman using statistical software. And the last one is interpretation and computation of coefficient of determination. Okay, let us start our lecture with this question. Is there a relationship between pulse rate and systolic blood pressure of women? Or let us talk in general. Is there a relationship between X and Y? Between X and Y in general, is there a relationship between two variables X and Y? So the answer of this question is a key point in the correlation analysis in statistics. Okay, correlation concerned only with paired data. Okay, so with this paired two variable data, is there a relationship? Is there a correlation, or is there association between these two variables? If yes, what is the strength of the relationship? So the general idea of the correlation is to examine, number one, if there is a relationship between two quantitative paired data. If the answer is yes, there is a relationship, so what is the strength of this relation? Definition: a correlation exists between two variables when one of them is related to the other in some way. This is a definition of the correlation concept in statistics. Correlation again exists between two variables when one of them is related to the other in some way. We use a scatter plot. To assess or to identify if there is a relationship between two variables. Scatter plot is a graph in which the paired XY sample data are plotted with a horizontal x-axis and vertical y-axis. Each individual XY pair is plotted as a single point. Scatter plot is a type of graphs, okay, representing paired in points. So this is X and this is Y variables. So we plot each point, or each point represents a paired, okay, paired values of X and Y. This is an example of a scatter plot. This is the variable in horizontal axis and variable of x-axis. This is X, this is Y, and the points represents the paired data of each variables. Okay. Here, here we have different patterns or different structures of the scatter plot. For the first one, for example, the points represent a straight line. Okay, when points of xy represent a straight line, this is called perfect. Okay, perfect correlation. The perfect correlation can be positive or negative depending on the slope of the straight line. So here we have positive slope, straight line. That means we have perfect positive correlation. The same for negative correlation. We have negative slope. Points represent straight line. So this is perfect. This is perfect negative correlation. It means that there is 100% negative correlation between x and y. So increasing in x implies decreasing of y. Okay, this is a negative correlation. Positive correlation means increases of x means increase in y, and so on. Here we have a pattern. We have a pattern of positive correlation, but the correlation is not perfect. Okay, because the points are not fall in the same straight line. So this is strong. Okay, this is approximately strong. Sorry, it is negative, strong negative correlation. Okay, it is a pattern of negative correlation, but not perfect. Okay, here we have different pattern of correlation between x and y. Okay, the points here doesn't represent a line. Okay, not like here and in strong negative correlation. It represents something else. Okay, something else. So this is quadratic function. This is an example of quadratic function. You know, quadratic is y equal x square. Okay, y equal x squared. Anyhow, this is something different, not linear. Okay, we mean linear means that the points show approximately a line. Okay, or approximately a straight line. Okay, either this straight line is perfect or is not perfect. Here we have random values, random points. So here we have no correlation. Also here the points show horizontal, okay, straight line. So this is also we have no correlation, because if you see here we have only one value of y. This is why we have only one value of y for different values of x. So here we have no correlation. Anyhow, we use scatter plot to identify, to illustrate, to show, to examine if there is linear correlation between x and y. Okay, examining relation between blood sugar level, which is y, and body mass index in the file diabetes.gump in GUMP software, and answer the question that is there a linear relationship or no. We use, as you know, we use a scatter plot to examine or to identify if there is a linear, okay, relation between the two variables. Here we have y, which is blood sugar, and body mass index for a sample of patients. We should have paired quantitative variables. We should have paired quantitative variables. Okay, here this is body mass index, and this is y, which is blood sugar, and this is the pattern. Okay, the pattern of relationship between the two variables. Yeah, the pattern doesn't show straight, okay, or perfect relationship. Yeah, but there is a sense of linear correlation. There is a sense of linear correlation as the points show approximately a pattern of linearity. So as is positive, there is a positive linear relationship between blood sugar y and body mass index, but the relation is not perfect. The relation is not strong, okay, because strong means the points are closer together. Okay, the points looks closer. This is for strong. This is not strong, not perfect, but still there is a sense of positive relation. Okay, to subjectively judge about the correlation, we use a measure called linear correlation coefficient, small r. Okay, the measure called linear correlation coefficient, small r, to measure the strength of the linear relationship between x and y values in a sample. Again, the linear correlation coefficient, small r. It is a very important measure in statistics, measures the strengths. Okay, so the objective of r is to measure the strengths of linear relation. So to compute r, we should first ensure that we have linear. Okay, we have linear relationship between paired x and y values in a sample. So again, r, small r, is something called linear correlation coefficient. This linear correlation coefficient used to measure strength of what? Of only linear relationship between paired x and y values. This is a general guide for explanation of the value of r. So this is a small r. Small r lies between less than or equal 0 and less than or equal 1. So it lies between 0 and 1, positive or negative. In general, if r is at least 0.8, that means 0.8 up to 1, sorry, up to 0.99 or so on, we have very strong correlation. If r is somewhere between 0.6 and 0.8, we can say that we have moderately strong relation. If r is between 0.3 and 0.5, we can say we have fair correlation. Otherwise, less than 0.3, it implies poor relationship between x and y. The same can be applied for negative values. Okay, for negative values. We have statistical assumptions to compute small r. Number one, the sample of paired x, y is a random sample. This is number one, random selection. Number two, the pairs x, y have bivariate normal distribution. That means this measure r is a parametric. Okay, it is a parametric measure. Okay, so it is required normal distribution. Okay, here we have the notations. Small r, small n, you know, is a number of pairs. Okay, presented in data. Summation, sum x, you know, the sum of all x values. Sum x square, sum x all square, sum x y, r and rho. Forget about these notations because we are not going to manually compute small r. Focusing only on small r, which represents linear correlation coefficient for a sample. This is important. Okay, small r is related to sample, so small r is a statistic. Okay, it is a linear correlation coefficient for a sample. This notation is called rho. Okay, this is called rho. Rho represents linear correlation coefficient for a population. So rho is the corresponding parameter of a small r because rho represents linear correlation coefficient for a population. This is very simple example. Here we have x and y. We have paired data for x and for y. You know, n equal number of pairs, n is 4. So this is x, y, x times y, x square, y square, and so on. And these are the summations. This is a formula for computing small r. Okay, r equal and so and so. Don't care much about this formula. We are not going to manually compute small r. Okay, the final answer, r is 0. minus 0.135 or negative 0.135. The negative signs indicates negative correlation. But the value itself, which is 0.135, it is less than 0.3, So we can say we have poor, okay, we have poor correlation between x and y, poor negative correlation between x and y. Okay, here we have properties of linear correlation coefficient small r. It is very important. Okay, number one, you know, r lies between -1 and +1. You know, +1 indicate perfect positive correlation. -1 indicates perfect negative correlation. Number two, values of R does not change if all values of either variable are converted to a different scale. It means that if all x's and all y, okay, values are converted to using the same value, R does not change. For example, if all values of x are, or if we add, let's say, a constant number a for all values of x and adding also a constant number a for all values of y, still R remains the same. Number three, R is not affected by the choice of x and y. Interchange x and y and the value of R will not change. Okay. In calculation, if we use x, the values of x instead of the values of y in the equation, or vice versa, also a small r will not be changed. That means it doesn't matter which one of x and y is being horizontal or vertical axis. Number four, R measures strength of a linear relation. This is important. Okay, R is valid only for the linear relations. That means it is meaningless to use R or to compute R if the relation between the variables is not linear. Okay, here we have R square. Okay, when squaring the value of R, we have R square. R square in statistics is called explained variation, or it is called coefficient of determination. The same. Okay, R square is the explained variation or coefficient of determination. The value of R square is a proportion of the variation in y, the dependent variable, that is explained by the linear relationship between x and y. Or we can say the value of R square is a proportion of the variation in y that is explained by x. Okay, the same. So this is the definition of the coefficient of determination, which is R square. This value, R square, is called coefficient of determination in statistics. So what is coefficient of determination? It is R square. It is the square of small r. What is the small r? Small r is the linear correlation coefficient. What is the explanation? Okay, what is the definition of R square? R square is a proportion of variation in y that is explained by the linear relation between x and y. For example, quick example, let's say x represents number of hours, okay, of reading, okay, for a selected sample of students per day or per week. Anyhow, this is, for example, number of hours of reading by students. Student 1, for example, read 2 hours per day, and y represents the score of students in certain course or in DBA. Anyhow, for example, y is the scores, okay, for the first one, 2 hours reading and 67 score, okay, or somehow the second one, 71, and so on. Okay, we have a sample of x and y. X represents number of hours of reading, and y represents the score of students in the course. Okay, let's say that small r, which is the linear correlation coefficient, which is computed for linear relation between paired x and y. Let's say small r is 0.78, for example, 0.78, which is indicate a strong correlation between x and y, strong and positive, indicating that increasing x, which is number of reading, lead to increase in y, which is score of students. Okay, now let us compute r square. Okay, r square, which is 0.78 square. R square is 0.61. Okay, 0.61. So 0.61 is the square of 0.78. Okay, What is 0.61? 0.61 is the coefficient of determination. And what is coefficient of determination? Coefficient of determination is the proportion of variation in y, okay? That is explained by a linear correlation between x and y, or explained by x in general. Okay, so 61 means, in this example, we can say that 61% of variation, okay, in students' score is explained by this factor or by this variable of time of reading. Okay, again, 61% of variation between students in score is explained by the linear relation between x and y, or it is explained by x, or it is raised to, or raised to variation in x. So in other words, x factor or variation between students in reading responsible of 61% of variation in scores. Still we have 39% can be explained by other factors rather than time of reading. Here is an example, or let's say we have pots, number of pots, and number of manatee in some area, manatee deaths. R is calculated to be 0.922, which is very strong positive correlation. R square is 0.85, so we conclude that 0.85, or about 85% of the variation in the dependent, which is manatee deaths, can be explained by the linear relationship between the number of pot registration and the number of manatee deaths from the pots. It implies that 15%, the remaining, of the variation of manatee deaths cannot be explained by number of pot registration. It is due to other factors. Now, testing the significance of the linear correlation coefficient. Okay, we wish to determine whether there is significant, is this correlation of coefficient significant or no. So here we are going to use hypothesis test for testing the significance of linear correlation. We need to set H0 and H1. Okay, H0, which is the null hypothesis, rho equals 0. It means no significant linear correlation. And you know, we use rho and not small r because testing hypothesis is concerned with parameters and not statistics. So we use rho, which is a parameter of linear correlation. H0, rho equals 0. No, means that no significant linear correlation. H1 rho is different from 0, okay, which means significant linear correlation. Okay, let us see how to use the software to generate the output regarding linear correlation. Here we use again Y, which is blood sugar, and body mass index. This is the independent, this is the outcome. Number one, what is the strength of the relationship? Okay, so to answer strength of relationship, it means that we need to compute small r. Okay, small r is a measure, okay, used to measure the strength of the relation. Number two, what is the direction? The direction depends on the sign, of small r, if it is negative or positive. Okay, does the significant linear relationship exist between two variables? So here we need to answer this significance, to answer the question about the significance. So that means we need to see the hypothesis test. Okay, what proportion of variation in y explained by the relation? And you know the proportion of variation is computed by computing r square. Okay, r square, which is a determination, okay, which is a coefficient of determination. This is answers the question about the proportion of variation. So you need to compute small r, see the sign, then test the hypothesis and find R square. Let's say this is the output of Pearson correlation. This is linear correlation. It's called Pearson. This is the statistician Carl Pearson who developed this measure. Anyhow, here we have the results of correlation. You know, Y and body mass index. C, the interaction between Y and B body mass index. The value is 0.586. This is a small r, 0.586. We can say that it is fair. No, it is moderately. Yeah, it is moderately correlation. Okay. Also, with the results, we have the probability. This is the p-value, of the significance test. So this is the p-value of the correlation coefficient, which is less than 0.05. It is something very small, 0.0001. Again, take the value of small r and take the value of the p-value of correlation. Okay, what is the strength? Pearson correlation coefficient, which is small r 0.587. Therefore, there is the strength of linear relationship is moderately strong. Okay, depending on the value, it is moderately strong. So this is the answer of the first question. Second, what is the direction? Okay, as the sign is positive, we have a positive. So we have a positive correlation. The direction is positive correlation. It means that as one variable increases, as x increases, x is body mass index, the other variable increasing, which is blood in sugar, y. Okay. Does a significant linear relationship exist between the two variables? You know, we use the p-value of the test significance test. P-value is less than 0.05. So our decision is reject the null hypothesis. P-value is 0.001, which is less than 0.05. So we reject the null hypothesis, which means that there is significant linear relationship. So the correlation is statistically significant. Number 4, what proportion of variation? You know, proportion of variation is a coefficient of determination, r squared. So r squared is 0.587 squared. The answer is 0.345. It means that, or it can be explained that 34.5% of variation in y, which is blood in sugar, is explained by the relationship with body mass index, or is explained by the factor, which is body mass index. In other words, body mass index is responsible of about 34.5% of variation among patients regarding blood in sugar. Now, let us move to the second part of this lecture, which is about rank correlation. And you know, from the name rank correlation, this is a corresponding non-parametric. Okay, this is corresponding non-parametric measure of correlation. It is non-parametric. So, rank correlation uses ranks of sample data consisting of matched pairs. So, in rank correlation, we use rank instead of the crude value in computing the correlation. The rank correlation test is used to test for an association between two variables, the same. This is a testing hypothesis of rank correlation. We can see later. Rho S is for rank correlation of population. It is the same like rho in linear correlation. And rho S doesn't equal 0. This is a test of hypothesis. I think this is not the appropriate place of this point. Anyhow, you know, advantages. These non-parametric methods, like all non-parametric methods, can be used in wider variety of circumstances than parametric method of linear correlation. With rank correlation, we can analyze bare data that are ranks or can be converted to ranks. Okay, so it is like all non-parametric methods can be used in wider variety of circumstances.
Number two, rank correlation can be used to detect some and not all relations that are not linear. Okay, so this is one of the main advantages of rank correlation. Sometimes it's used to identify or to detect some relations that are not linear, because when the real data show non-linear, the real values of x and y show non-linear relation, we can convert, okay, we can convert uh, the data into ranks and show the relation between them. Number three, the computations of rank correlation are much simpler than computation of linear correlation, as can be readily seen by comparing the formulas. Anyhow, I think this is not cannot be considered as advantages, because in most cases we use software, okay, to generate the value of rank correlation or linear correlation. Now, the disadvantage is that rank correlation of rank correlation is efficiency rate, which is 0.91, as you have seen before, okay, in the comparison between parametric and non-parametric. You know, all non-parametric measures are less efficient compared to parametric ones. Now, here is small rs, which is the rank correlation coefficient of the sample. Okay, so small rs is corresponding to small r. Small r is the sample linear correlation, and small rs is the rank correlation coefficient. Rho s is the rank correlation coefficient of population, so it is similar to rho, which is the population linear correlation coefficient. So be careful. Here you have, still now we have R, we have RS, we have rho, and we have rho S. Okay, R is the linear correlation coefficient for a sample. RS is the rank correlation coefficient for a sample. Rho is the population linear coefficient, and rho S is population rank correlation coefficient. Okay, so RS is often called Spearman. Okay, so the statistician who developed rank correlation is Spearman. It's called Spearman. Okay, again, using GUMP software, uh, we want here to see or to examine the correlation between RAM pulse and max pulse for a sample of individuals. Number one, strengths. What is the strength of relation? Number two, direction. Number three, significance. Okay, this is using Spearman rank correlation in statistical software GUMP. This is this part is about linear correlation. Okay, so ignore about this part. Look here, we have non-parametric Spearman rho. We have non-parametric Spearman correlation. Okay, these are the variable max pulse and RAM pulse. This is the Spearman coefficient. Okay, the Spearman correlation coefficient is 0.932, and this is the b value. Okay, this is the b value, which is less than 0.0001. This is very small value. Again, non-parametric Spearman, C, the Spearman correlation and the b value. So we can say that Spearman rank correlation coefficient RS is 0.932. Therefore, the strength of the relation is very strong. You know, if the value of small r is greater than 0.8, we can say we have very strong. What about direction? Positive. As one variable increases, the other variables also increases. We have positive correlation. Okay. Does a significant relationship exist between two variables? Again, the b value is less than 0.05. We reject the null hypothesis. So there is significant relation or correlation. There is significant relation or correlation. Okay. Here we have an important point. is about common errors involving in correlation. Yeah, it's common errors related to correlation. Number one, causation. It is wrong to conclude that correlation implies causality. Okay, this is important. Correlation does not mean causality. In other words, if there is correlation, significant correlation between X and Y, it is not correct, okay, to say X causes Y. Okay, again, if there is a correlation between X and Y, it is not correct. It is wrong to say that X causes Y. But the right way to explain the correlation is to say that there is a relationship, there is a correlation, but it doesn't mean X is a cause of Y. Okay, no. Number two, using averages suppresses individual variation and may inflate the correlation coefficient. Okay, very simply, if we use averages and not crude data, that means if we sum values in averages, the R will increase. Okay, small r will increase. But using the real or the crude variable values of variables give different value. Okay, linearity. There, there, there may be some relation between X and Y even when there is no significant linear correlation. Maybe the correlation between X and Y is not linear. Okay, is not linear. That means there may be some other non-linear relation between X and Y, even if the significant linear, if we have no significant linear correlation. For example, here we have no significant linear correlation, but there is a pattern. There is a pattern of correlation between X and Y. This pattern is not linear. Okay. Here we have, or you can see jump exercises. Example, for scatter plot between Y and body mass index. Also between Y and body mass index, answer strength, direction, significance, and proportion of variation. The way of finding results. Here are the findings, that is the same. Okay, the same for Spearman rank correlation. Here we have steps to generate the outcome and how to explain the results. Thank you very much. Exercises will be uploaded regarding this lecture. Assalamu alaikum.